All right, good morning and welcome to today's webinar titled Maximizing Efficiency and Productivity of Aluminum Hot Stamping, presented by Schuler and hosted by Metal Forming Magazine and the Precision Metal Forming Association. My name is Brad Kuvan. I'm the editorial director at Metal Forming, and I'm pleased to be today's moderator. Before we get started, just a couple of notes about the meeting session today. The meeting is being recorded for archiving, and the recorded event will be posted to our website within the next day or two. We'll let you know via email when the recorded webinar is available for viewing online. Also, all the participants in the meeting today are in listen-only mode. That means that the speaker and other listeners will not be able to hear audio from your site during the program, but you do have the ability to communicate with us throughout the program by submitting your questions and comments using that question box, which is located on the bottom of your Zoom screen. You'll also use that same question panel to ask questions of our speaker at the end of the presentation. So now it's time to begin today's webinar. Today we're going to learn about a recently developed industry process for aluminum hot stamping. It's called FAST, which stands for Fast Light Alloys Stamping Technology. And we're going to learn how this FAST technology compares to conventional hot stamping technology that's currently being used for aluminum forming. So the webinar is going to address a few key benefits that metal formers can expect from this technology. Those include volumetric efficiency, energy savings, as much as 80%, and a press cycle time reduction of 10 to 16 seconds per part. So joining us today from Schuler is Jens Asbacher. Jens is the Senior Sales Manager for Hydraulic Presses at Schuler and is an expert in hot stamping. So please welcome Jens.
So welcome everybody to our webinar today. I'm pleased to present here this new technology in the North American market. To start with the topic, just let me give you a short introduction of the development of high-strength aluminum and also the first interactions between with Schuler with high-strength aluminum. And you can see on here some pictures, and there is a nice story behind this broken Zeppelin. This happened 1909, was one of the trip of the LZ5 coming from Friedrichshafen in Germany, and they wanted to land near Göppingen, where the headquarter of Schuler is. And during the landing, they hit a tree and destroyed the nose of the Zeppelin, as you can see on the picture. And it was a bunch of Schuler people, Schuler employees, who helped to repair the Zeppelin. And they used wooden hopsticks to rebuild the nose of this Zeppelin, and they were successful, and they started again to fly all over Germany with this Zeppelin in a very early stage of the development of airships. And based on this experience, there was later also interference between Schuler and the company Zeppelin in Friedrichshafen. There was actually, and it still exists in our archive, there is a letter of graduate from Graf Zeppelin in person to Schuler to thank for the help they got during this landing. High-strength steel for aircraft industry has been developed by Claude Dornier. He was an employee from Zeppelin at that time, and he started to develop special aluminum alloys with a higher tensile strength to design the structure of the airships built in Friedrichshafen in Germany at that time. And it was also Hugo Junkers, 1919, he launched the first all-metal built airplane. It was the JUF-13, which was also one of the first airplanes which were used by the Deutsche Lufthansa for flights within Germany and Europe. And also Dornier itself, Claude Dornier itself, he founded later his own company called Dornier. And he built also in 1922 an all-aluminum airplane. It was actually a flying boat, which was very successful, produced in many countries in Europe. It was a licensed design, and it also offered the first postal service via the Atlantic Ocean in the 20s of the last century. So, and coming back to the story between Schuler and Zeppelin, it was so that some of the first high-strength aluminum structures were produced on Schuler presses, and Schuler delivered many of these structures to Zeppelin in Friedrichshafen. So this was actually our first experience with high-strength aluminum at that time. So later we also got experience in stamping of aluminum. This is one example here. Maybe you remember the XJ from Jaguar, which was an all aluminum car body. And at this time, when they started the production, they had no press shop. Jaguar had no press shop, and we delivered 2 hydraulic press lines to produce all the aluminum panels for this car. So this was also a very special experience for Schuler and also for Jaguar to start up this production. And also we still have applications for aluminum cold stamping. So you can see here a picture of our smart press shop, which is located in Halle in Germany. It's a joint venture between Schuler and Porsche. And you can see here on the right-hand side, that's an aluminum part. Yeah? And so it's a high-speed production of aluminum parts. With the Jaguar project, we still used hydraulic presses for the process. Here we have modern mechanical servo presses in use. They can run with a very high speed to produce these parts. It's a fully automated and connected production line. So that means they have a fully automatic die change. Even the crane is radio controlled. There is no man available on a die change. It's all automatically. And also this is kind of a showcase and a role model for all our industrial IoT solutions for quality and for maintenance as well. So these are our first experiences with aluminum. And in general, aluminum is still an important material for lightweight design. And lightweight design is still very attractive, not only because of making lighter car bodies to reduce the fuel consumption on gasoline or diesel engines, but also for the electric cars, that the weight of the car is important because you have to add a lot of weight for the battery. So you have to reduce the rest of the car to get more out of the battery, more driving out of the battery. So the factors which are important for lightweight design is the performance of the material, of course, the weight of the material, the strength, the manufacturing availability, how you can manufacture these materials, and then also the corrosion issues, painting issues, and even more aspects are important for select the right material. But I think the most important thing at the moment is the CO2 print of the material, because the car manufacturers, they are looking very deep into this to reduce their complete footprint, CO2 footprint of the car. And then, of course, the material is the key. So coming back to the aluminum hot stamping processes which are in use at the moment. And this is a process which is a traditional forming process for aluminum. That means you heat up the high-strength aluminum 6 or 7 series material. You heat up in a furnace, could be a roller hearth furnace or could be a chamber furnace. but it needs some jet heating in order to get the heat into the aluminum, because the aluminum has a mirroring effect and it's very difficult just to get in the temperature by radiation. So you have a special furnace to heat up the material. It takes 5 to 8 minutes to heat up the blank. And during that time, you face the effect of solution heat treatment. What's that? That means that the precipitations which are in the aluminum microstructure, which are responsible for the hardness of the material, they will go away during solution heat treatment. That means the material is very soft when you take the blank out of the furnace. Then you can perfectly form it, and then you quench it down, and then you have a perfectly formed part. But unfortunately, it lost all the precipitations and it's not hard anymore. So you have to run it through the next process, which is the artificial aging of the material. That means you put all the parts in a chamber furnace, and then you run it somewhere between 100 and 150 degrees Fahrenheit. You have it there, and this, depending on the material, somewhere between 3 and 8 hours to create these artificial aging process, and then the material is hard again. It's followed by the paint bake cycle, which is normal for the automotive industry. That means when the car is completely manufactured and or the car body is manufactured and will be painted, to dry the paint, it's also a heat treatment which has to be taken in consideration to the complete aging process. So, but the end product is again a high-strength steel with aluminum part. So, how does a production line look like for this process? And also Schuler has delivered presses for this process. Here you can see the example using a roller hearth furnace with jet heating. On the right side, you can see the principle of jet heating. It's more or less a hot fan, and you blow the hot air on the surface of the aluminum to heat it up quickly, because, like I said, just with radiation, it will be very slow and not very effective. So you can see on the left side a classical hot stamping line with a destacker area, then the roller hearth furnace with the jet heating on top, and then a centering station, hydraulic press with a feeder for forming and quenching, and then at the end you have the end of line conveyor to bring out the parts of the line. So this is a normal setup for the current process for aluminum hot stamping. So the idea from Imperial College in London, they have also developed this previous process to a certain stage, but they were not satisfied completely with the result. And so they said, we need to find further ways to hot form aluminum and to keep the strength of the material. And so what they did, they tried to heat up the material extremely fast to avoid solution heat treatment. And they also made a very precise study how to heat up fast. And the end result was that heating by contact between two heated plates, it's the only way that you can heat up the material in the time you need to keep the precipitates in the microstructure of the aluminum. So you can see here on the graph that you have a very fast heating up to about 300 or 450 degrees Celsius. And then you need a very, very short and fast transfer from the furnace or from the heating station into the forming die. And then you do the forming and quenching. And then the part is ready, and it has nearly the stiffness, the tensile strength of the ingoing material. And in connection with the paint bake cycle, you get back to the original material properties of the aluminum blanks. So, and this worked very good in a laboratory. The next slide shows you the test rig the Imperial College built to test this process on small samples. You can see here on the left side these red heating plates, and you can also see the sample here, this H-shaped blank. And then they have a forming station and a quenching station, and this green is the transfer. Of course, in a small test rig, in a laboratory, it works. Yeah, it's fast enough. So they tested this process for aluminum, different alloys of aluminum, also for high-strength steel, some thermoplastic composite materials, and also for magnesium. So, but in the further steps, they and we were focusing first of all on the aluminum. What we did, I mean, we were always in very close contact with the Imperial College, and when they showed us this process, we were very excited, but we had some concerns because due to this very short time frame we have for heating and transfer the material, we were really concerned that if this would work in a real part and in a real die in a press shop environment. So we decided to raise up a project with three parties. That was the Imperial College in London. This was a tier one supplier, Hanlai in China, and this was Schuler. And we had from our tech center in Göppingen, we still had our test die, which was a 3-station die for hot stamping. So we rebuilt this die, and as you can see in the left picture, with a heating plate, a small transfer unit within the die, and so we got this into operation. We did the trials at the Automotive Center Südwestfalen in Attendorn in Germany, where we rented a Schuler press. In this case, it was a servo press. And we did a lot of trials with different setups, with different materials, with different lubricants. Also, some OEMs were already participating who were interested in this process. And we used 6,000 serial aluminum, and also with a special pre-treatment at the material supplier. So that's the reason why we call it TX temper and not T4 and not T6, because it's something in between. And this is also one parameter which can be adjusted to achieve the results you need for your parts. So the thickness of the blanks for the trials was 2 millimeter. The heating temperature of the heating blade was 330 degrees. The heating time was about 4 seconds. It was actually related to the capability of the press, because it's not so normal for a servo press to stay under pressure in BDC. So we had to trick the control system a little bit. Then with our transfer, we could reach a transfer time of 2 seconds. And so we didn't lose much temperature. So the forming temperature was 320 degrees. And after the forming and quenching, the part temperature was 60 degrees Celsius. So in the next picture here, we can show you the movie. The blank has been put into the heating plate manually by 2 men, and then we started the automatic process. Now we move the hot material, and now we do the forming and quenching of the part. And in this case, we cool it down very far that we can take it out manually by hand. So this was actually our tryout setup. And during the last year, we did many trials, more than 600 parts we've produced with different alloys and different setups of lubricants. So we came to a very good result for this part. So here you can see some of the measuring results. This was the result of the measuring of the tensile strengths and the yield strengths. And you can see that we did it with different paint bake cycles and also different preconditions of the material. But you can see finally, if you get the right setup, you can reach again the 310 here, in this case, the 310 Newton per square millimeter, which was more or less the material property of the ingoing material. So how would a production line for this process look like? So we are far away from a traditional hot stamping line. It's more or less a transfer press, a classical transfer press, but not with several forming stations. It's with a heating station and a forming and cooling station. And if required, we even can add the trimming operations into this press as well. Of course, this is a different story because the cycle time of this transfer press will be somewhere between 10 and 16 seconds, depending on the size of the part and the thickness of the material. And a traditional trimming line for such parts normally runs much faster, nearly, well, more or less double the speed. So it's questionable if the trimming should be added there, but it's a matter of calculation. You can also take them out and trim them on a separate line. Yeah. But other than this is a traditional setup of a transfer press with a destacker. Here we have a loading station with a shuttle to move the part underneath the triax transfer. Then we have the classical triax transfer, which is moving the blank and then the part through the press and at the end out of end of line conveyor. And the end result of all these research projects we did together was that our customer Hanlai, they decided to invest in their first production line. So, and this is the next picture. This is how it looks like. It's an hydraulic 1200 ton press with 3 by 3 meter bolster size, classical destacker with the shuttle and the triax transfer mounted to the press. We have 2 moving bolsters for fast die change. And at the end of the press, there is a conveyor and then 2 boxes for unloading the part. So a classical transfer press design, nothing very special. It's a hot stamp. The drive of the press is a classical hot stamping press drive, servo controlled and extremely fast for the forming of the part. Then we use a triax transfer system and the classical destacker with a robot and a marking station, the end of line conveyor, and we also have the then the forming and quenching die, which has the heating plate and a lubrication unit. And this line will go in operation mid of this year in Guangdong in China, which is south close to Hong Kong. On the next page, you can see also the first die. You can see that we have selected a more complicated part for forming, which is a door inner, which is a very well-known part or very well used for aluminum, because most of the OEMs make their doors out of aluminum, and the inner door is always a challenge. And so we have selected the inner door for the next part. And here you can see on the right side the setup for the heating plate. In the middle, you can see the bar for the spray lubrication, and then the forming and quenching die with classical drilled holes for cooling down the pressed part. Yeah, so to sum up all the aspects, the big benefit of the process is that we don't need any furnace for heating up the blanks, and this will of course lower the operating costs and also the required space for the line. We can also eliminate the entire post forming process, so the artificial aging is not required. We still have the paint bake cycle, but this comes automatically with the painting and drying of the paint of the car body. So due to the fact that we very specific only provide the heat to the blank in a very small area, there will be a lot of energy savings. So the result of the investigations of the Imperial College was about 80% in comparison to the other heat treatment processes for aluminum. The press cycle is pretty fast due to the fast heating. We have, depending on the size and the blank thickness, 10 to 16 seconds cycle time per part. The process actually delivers extremely good formability of the material and especially a very good repeatability. So there is really, with very tight tolerances, there is one part like the other, which is not if you do aluminum cold stamping. So this is really a great benefit for forming this part. The trimming process, as I told, could be added directly to the transfer process, but this should be calculated carefully. I think it depends on the volume of the parts you produce. It could be more beneficial to run this on a separate, very fast trimming line, because 2 hot stamping lines could feed 1 trimming line. And then, of course, the equipment, I mean, it's still a classical transfer press. If you don't have the use for aluminum hot stamping, you can still use this press for traditional cold stamping of aluminum or other materials. Yeah. So, and I think the final strengths, again, from the incoming material, in our case, it was 320 Newton per square millimeter, comes after the paint bake cycle, and with the heat treatment of the painted car body. So in total, we have a lot of benefits for this process, and we think it could be very interesting, not only for the automotive industry, which is one of the largest user of aluminum, but also for the aircraft industry. And maybe this webinar also leads to the process that other industries look for this process for other materials and other products. Yeah, so this was everything from my side so far. So now you are invited to raise some questions if you have some. Thank you very much for listening.
Fantastic, Jens. Thank you for that really interesting presentation. And we do have some questions coming in, as I'm not surprised, since this is such a breakthrough technology. So we'll go through these questions. Can you tell a little bit more about how the heating station works? Share a little bit more detail.
It's actually pretty simple. We have 2 special steel plates, and they have drilled holes, and in those holes we have cartridges, electric cartridges. And so that means we heat up the heating plate to the selected temperature. Yeah, it's designed to heat up to between 300 and 500 degrees Celsius. So you can select, and then it's insulated around, so only the upper plate is facing the environment, and it's designed according to the size of the blank, so to minimize the losses of heat. And then, of course, if we press down, we need also high pressure to control the contact between the heating plate and the material. And then we keep it there for a couple of seconds, and it becomes very fast, very hot. Yeah.
Thank you. What are the production rates you expect Hanlai or others to
Yeah,
get
that's
from this process?
what we said. I think it will depend on the thickness of the material, yeah, because the heating time and the cooling time is by physics a function of the thickness of the material. And then, of course, the size of the part, yeah, because the transfer step will be also related to the size of the part. But we expect between 10 and 16 seconds for very large parts. This will be the production rate, which is, of course, for hot stamping extremely fast. Yeah.
Okay,
Including the heating, we have to consider.
good, thank you. The aluminum temper, is it T6 that they're getting from the mill?
Yeah, that's what I said. It's between T4 and T6. So what we did for all the trials, which we did for OEMs, they told us which material they want to use and what the result they expect. And then we did some pre-trials in the laboratory of Imperial College to find out the right temperature recipe for this material. And so it's some condition between T4 and T6. It's not really defined, and it's also part of the technology that we can actually more or less design the material as we want. But of course, we have to integrate in this design the material supplier because of the pre-treatment at the material supplier.
Okay. All righty. Questions are still coming in. Does the bake cycle change the dimension of the part as the strength changes?
No,
Okay.
because the paint bake cycle is, I mean, we have already a complete welded and painted car body. Yeah, so it would be very critical if the form would change. So because the heat treatment is very low, we only have there will be some more precipitations coming out and make the material harder, but there is no form change of the material.
Okay.
Of the part.
What about strength loss from the as received material to stamped?
I mean, of course, when we take out the blank of the heating plate, then it's soft. It's not as soft as after solution heat treatment. Yeah? And you can see also different if you heat up only to 280 or maybe 350. This is also a parameter where we can play around with. Yeah? If we have extremely complicated forming parts, we can raise the temperature to 350. If we have simpler parts, we can just leave it at 300 degrees. But it's soft enough to be extremely good formable. And yeah, that's it.
But I think the question is, once the part is stamped prior to paint baking,
Okay.
what's the strength loss compared to as received?
It's about 10 to 20%. Yeah.
Okay.
And this we gain again when we do the paint bake cycle. Yeah.
So compared to the HFQ process, which we talked earlier about, also came from Imperial College, is the main difference then that fast does not solutionize, if that's the word, the aluminum?
Yeah, of course. I mean, we don't proceed this solution heat treatment. Yeah, so we don't lose the strength of the material. Yeah, because it's just everything happens too fast that the material actually could react. Yeah? And because a solution process always needs time, yeah, that the atoms can move. So this is the physical basics, but of course the result is complete different heating technology, no aging required. So we think there's a big benefit. We might not can provide every part with this process, because of the size, and maybe some parts need solution heat treatment because of the very complicated form they need. But this we will see in the future. Yeah.
What about the reflectivity of the aluminum? 6000 series and 7000 series have different reflectivity. Um, does that need to be accounted for in the process?
You mean the reflection of the heat, or
I guess that's what he's getting at with the reflectivity of the
because we
material.
with the
Yeah.
contact heating we don't care about the reflection,
Okay.
because we don't need this physical aspect. It's important for jet heating,
Okay.
but not for contact heating.
Gotcha. After post heating, does the part geometry change much?
No, there are no changes anymore.
Okay. What about lubrication? The question is, does the process require lubrication? I'm sure it does,
Yeah,
and I
I
think you
mean,
showed a loop station on the diagram there.
yeah, we did several trials, but I think this is also a key aspect of the whole process. Yeah. But this is true for every aluminum hot stamping process, that lubricant is the key. So we have tested several lubricants. We have one favorite at the moment, but we will keep on testing different lubricants, and also uh, spraying systems, spraying on the blank, spraying on the die. Our line is quite flexible on that. We can install different things, and I think this will be one of the next steps for the future in China on the line there, that we go ahead with finding the perfect lubricant. Maybe for different materials, we also need to have different lubricants.
And you said you're spraying. Did you try the roller application or no?
Uh, so can you repeat? I didn't.
For applying the lubricant, you mentioned that you're spraying the lubricant
At the
onto the
moment, we are
material.
spraying. Yeah, that's the. I mean, the problem is we don't have much time to spray or to put the lubricant on the blank, because of the fast transfer, and it doesn't make sense to put the lubricant on before heating, because then the lubricant will stick to the heating plate and will be not on the blank. So doesn't work at all. So we have to spray it, and this is also the challenge, that the time frame to apply the lubricant is extremely short. But so far with this part we made, it worked, and but we will further work on this to find the right way.
All right. Hang in there, Jens. We got lots of questions. So I'm sorry, this is a comment and a question. So contact heating is usually not uniform. Is that something that you're struggling with? And he talks about smear and damage to the surface, which I'm not really sure what that is. But how are you avoiding the damage to the surface during the contact heating?
I mean, uh, due to these temperature difference of only 300 or 350 degrees, the growth of the blank is not so big that we get a real damage on the surface of the material. We got more damage in the forming than in the heating, and we use a special material for the heating plate, and we also have a special unit below the heating plate to make sure that we have perfect contact over the whole blank. And this worked actually very fine, because the temperature of the blank was quite even over the whole blank.
You talked about trimming. Can you do all of the trimming in the die, or are there still some areas that need to be laser cut or trimmed in some other process?
I mean, the trimming is a normal cold stamping process. I think every trimming which can be done mechanically with a trimming die could be done. Like in cold stamping, you can split it in 1, 2, 3 operations. You can even turn the part if necessary to get a different trim direction. I think that's exactly the same, and it is cold stamping because the part is cold already. We don't do hot trimming.
Okay. Can you compare the mechanical properties of the stamped part, tensile yield and elongation? Compare those properties to a solution heat treated application?
I think if it's the same material, you can compare it. What's not possible is to increase the material properties due to this process. So the process can only manage to reinstall the material properties of the ingoing material. We cannot change it very much to make it harder also. I don't know if this is possible maybe with the solution heat treatment process to increase the strength of the material.
So there's a question about I guess the consistency of the temperature being applied to each subsequent blank. And I'm assuming that you heat each blank to the same temperature.
Of course,
yeah. So the heating system has to recharge.
Exactly. So that means, of course, there is a lot of heating power installed because as soon as the press opens and the blank goes out, we take some energy out of these plates, and they have to be reheated to the set temperature in a very short time before the next blank comes in. But I mean, I think we have a good relation between installed heating power and size of the blank, so it works fine.
Okay. Can you talk a little bit about what you've experienced so far, or Hanlai has, in terms of the maximum blank size and thickness that y'all have worked with so far?
We have not tested too much different parts because we only had this one die. The next step is this inner door, which is for the equipment we have. It's the maximum what we can do. It's about what is it? I think 1.3 by 1 meter, and also we'll have thickness somewhere between. We'll start with 2 millimeter, but maybe we'll then go down a little bit to because normally door inners are not at 2 millimeter; they are a little bit thinner. But that's also on the list for the next steps to try different materials, thicknesses and sizes. But there is, of course, a physical limit for size, but this is not of the fast process, it's also of the transfer process, because you can only handle part with this triax transfer, and there is a limit. So you will never run a double dooring with this process, because you cannot handle it with a triax transfer. And also the step for the transfer will be very long, and I'm really doubt that then the process will work because the timing will not fit. So there are some physical limitations to the process as well.
Was process simulation done at some point at Imperial or at Schuler?
Yeah, we did forming simulation, but not the whole process, just the forming of the material.
Okay. And was there pretty good correlation between the simulation and the actual?
This we can tell you end of summer when we have made the first parts, because we did the simulation of the inner door, and used this simulation to optimize the parts that we can manufacture it, and the thinning is okay, but the verification is at the moment not done yet. The die is just in the manufacturing stage.
And I think you did mention you can do 7,000 series with this as well as 6,000 series.
Yeah, we did some tests. It worked good so far, But all the interested customers, they were concentrating on the 6,000 material. Yeah, we did tests with different versions of the 6,000, and so we were concentrating on this. But the trials we did with the 7,000 material, they worked quite well. Yeah.
Are you willing to share any more about the lubricant, the type of lubricant that you've settled on to this point?
To be honest, I really don't know what is
Okay.
what is the brand of the one we're using at the moment. Yeah, but yeah,
Okay.
we will figure out. Yeah.
And is there a tool coating required? Do you know if
It's
they're coating the tool?
difficult. Yeah, we tried some coating. To be honest, it was worse than without coating. So, but we will test more coatings, yeah, because we are still open. But the coatings we tested so far, they weren't very successful. Yeah.
Okay, so in the past, projects with contact heating to 500C resulted in aluminum oxide formed on the blank, which then transfers to the tooling. Are you finding that the lubricant that you're using reduces that aluminum oxide transfer to the tool? Do you know if that's
It's
been an issue?
hard. I think we have done not enough production to really see this. Yeah. So I cannot tell
Okay.
anything about it. Yeah.
Spring back, is there any spring back at all, or
No, like I said, the repeatability of the part is excellent. Yeah. So we did a complete measuring round of I think 200 parts we measured, and they were in an extremely tight tolerance in respect of foam tolerance. Yeah.
It's an interesting question. Can you do, multiple parts out of the tool, or is it really just going to be one stamping?
Yeah, it's whatever you can do with a triax transfer system. You can make two parts double attached. Yeah, they will be connected in the center. You can make a small part left and right with one blank, and then trim it later into two parts. That's possible, but you cannot do it like you have it in classical hot stamping of steel, that you have four parts in one batch. That's absolutely not possible with the transfer process. Yeah.
Right. Okay.
Because if we
Okay.
start to use robots or feeder or whatever,
Sure.
then the time between the heating plate and the forming is much too long, and then the whole system will not work anymore.
Can you pre-treat the blank prior to the heating cycle
Yeah,
in the tool, or does that?
yeah, but of course there is a pre-treatment at the supplier side. Yeah, but you cannot. I mean, you can if you want to save energy in the heating plate. If you preheat it, then you start already changing the microstructure of the aluminum, and you start then I think it doesn't work. You have to go from room temperature to the set temperature within seconds. You need to reach minimum 50 Kelvin per second heating speed.
Okay. Can you explain a little bit more about Schuler's role as this process ramps up over the summer at Hanwei? Are you supporting them, or just you just supplied the press? I think I know the answer to that.
No, we did all these trials we did together. Yeah.
Yep.
So we were more or less supporting the industrialization of the process with our tool, with our engineers, with our effort. Yeah. We have organized all the trials. And then, of course, now we build the equipment. We built the press. It's just started to be assembled at the customer side. The transfer is on the way on the ship to China, and the die is still in the die shop in the manufacturing place. So everything will come together in China in summer. And then, of course, I think we will stay there, and we will show use this as a showcase for final customers, for OEMs. We will produce videos and do a lot of tests about for the dyes, for the dye materials, for the lubricants, whatever. Yeah. So there is still a way to go, but I think the results we have so far are extremely interesting, and I think it could be a very good product for the future. Yeah.
Interesting question. Are you considering using this process for steel hot stamping?
Yeah.
Extending the, yeah.
Yeah, we did some. I mean, the basic tests has been done at the Imperial College. We did some tests with our hot stamping die with high strength material, which we heated up to about 500 degrees. It was quite good formable, but then we stopped with these trials. Because we were afraid that we will damage our die, because it's an hot stamping die designed for soft forming material and not for high strength material. And because we needed it for more trials, we didn't want to destroy it.
Sure.
But it's already on the agenda also for China, that we will test the process also for high strength aluminum, because it's also a good application to. You have a hard material, a hard blank. Yeah, you just heat it up quickly to a temperature which gives you enough formability, and then you quench it down again, so you can avoid all the spring back which you have normally if you form high strength steel material in cold condition.
Yeah. Is it difficult to with those large blanks, a door inner blank, for example? Is it difficult to keep the temperature consistent throughout the blank using that contact heating?
I mean, it worked for the first part which we showed, this sill beam. Of course, for the door inner, we can answer these questions in summer when we have heated up the first blanks with it.
Do you know what kind of tool steel they're using in the die section?
No, it's not a secret, but to be honest, I don't know what they have now exactly selected. We just had to made sure that the heat transfer coefficient of the steel from the tool steel and the heating blade should be similar because of the timing. Yeah? It's a transfer process, and the heating and the quenching will get the same time. Yeah? So we have to bring in the energy and take out the energy in the same time and the same amount. Yeah?
Gotcha. Okay. Is that door inner that you showed, is that an actual OEM inner? Or
It's a real part. It's an actual part, but it will not go into production. Yeah.
Okay.
So that's also that we selected this, that we can show it. So there is no secret.
Okay. Forming tonnage on that door inner. Do you know what the forming tonnage was? Is there any concerns with offset loading?
The press has a parallelism control system. Of course, because the forming and the heating will be in a different on a different point of stroke. Yeah? So we have the forming. The tonnage is not very high for forming, but it's off center, of course. And for that reason, we have a parallelism control system. And then the tonnage is the 1200 tonnage are far enough for the forming. For the heating and for the quenching, when the die is closed, the 1200 ton it's the limit for the door inner. Yeah. So if we have to produce larger panels in future, then you should have a bigger press with more tonnage and also more bolster size. Yeah.
Okay. Does the temper on the material have a shelf life In other words, do you have to use the material within a certain period to get optimum results?
I think this could be answered by a material supplier. I got the answer. There is no limit. Yeah.
Okay. 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 We're getting towards the end here. For continuous operation, do you think the blanks could be heated effectively using a renewable energy source? Okay. Good question.
Yeah, you can, of course, it's electric heated. Yeah, just put a windmill next to the building and then you have green power, no problem. Or put solar cells on the roof of the hall.
Yeah.
Everything is possible.
How quickly can you go back to that video? Can we see the video one last time? And then I think we'll here we go.
So the blank was already on the heating plate. We put it on there manually. So the heating is done. We transfer the blank. So you can see it was an extremely short time to heat up the blank from room temperature to 300 degrees Celsius.
Okay. So you and I talked about this a little bit earlier today, the potential for the technology in the North American market. You're obviously going to be introducing that to the market. Talk a little bit about the timing of that and where you see the potential for the technology in North America.
I think the great potential is in the automotive industry because it's the largest user for aluminum so far. But like I said, we're already in contact with some aircraft manufacturers or suppliers to the aircraft industries. They have their special materials. We are testing these materials at the moment at the Imperial College in London to make the more or less the pre-setting for the process, and it looks quite promising. But I see this also for whatever, where it's always when you need heat treatment of aluminum and when you want to produce a aluminum part out of high strength aluminum, which is not cold formable, then it's one solution, and so it could be in any industry. Yeah.
Very good. Okay, Jens, I think we're good. So thank you so much for handling all those questions and really a really informative presentation. To everyone in our audience, thank you for attending the program today. We hope you found it to be interesting and valuable. And again, an archive of the webinar will be available on our website soon. You'll get an email from us to let us know about that. And we'll also be able to share a copy of the PowerPoint as saved as a PDF. Then you'll be able to review what you learned today and perhaps share it with others within your organization. So again, thank you for joining us. Jens, thank you so much. And Schuler, thank you for sharing this with our audience today. Everybody have a great day. You can close your browsers now.
Also, thank you from my side for listening, and also Brad for organizing this webinar. Thank you very much.
Great job.